with you. Just in brief, I am a PhD student in my third year at RMIT University in an interdisciplinary School of Global Urban Social Studies and School of Mathematical and Geospatial Science. So today my talk isn't really core methods or algorithm or modeling. It's more about the journey in spatial research, where I have learned the capabilities of using AI and the application and harnessing the power of it. So as days goes, we are now moving from maps to use AI in our modeling and spatial research. So I'm gonna share that journey with you today. So before I start, as you can understand, I am from geography background, not computer science, not data science, pure geography background, and I love researching about landscape, climate, heat, environment, people. It really interests me because it's so many things are connected. It's not about where things are, but also how people interact with it, how people engage with it. And another very important thing that motivated me when I was doing my bachelor's in geography about sustainability, because you see, our cities are going so dense. It is so vertical. And for this, we are facing so many urban issues like rising temperature, we call it urban heat island, and there is land degradation and unequal access to nature. So how can we solve these questions? So we generally use map, but maps are limited. So that's where AI, algorithms, technology comes in to help us answer those questions. And that actually what motivated me to pursue Masters in Geospatial Science. And today I'm gonna share two of my research that I did in my Masters, and then moving on to PhD. And I can show one or two videos I have as a research associate that we have done on different technologies. So, okay. Before I talk about my research, I want to show the gap which actually exists in our spatial domain. We talk about our city is green, right? And you will always hear planners and practitioners, they use city scale maps, they use greenness measures, they use metrics called NDVI, which is just normalized difference vegetation index, to tell you how much greenery is there in the neighborhood. But look at the image closely. These satellite images that we use have different resolution. One can be 30 meter by 30 meter, one can be 100 meter by 100 meter. So the coarseness of this data set varies. So let's take 30 meter by 30 meter here, which is around 900 square meter, right? And in this 900 square meter, it's actually showing that there is green, right? There is high green. But we can't say what green is it. Is it trees? Grass, shrubs? When we zoom into a satellite image, we can find, oh, there's a bunch of trees. What type of tree is it? Is it different species? What kind of species and how it's impacting? So that's why my talk is based on why maps aren't enough, because for decades in spatial research, we have used maps to understand this kind of data sets, to analyze the pattern. So before I go to my research, just out of curiosity, I want to kind of ask you, how much are you familiar with GIS and geospatial research? Have you heard about it? So for those who don't know about GIS or geospatial science, in simple terms, we work with data set to understand the pattern and how it changes over space and time. So we use like aerial images, satellite images, we use statistics to understand the relationship, we use machine learning to detect the patterns, to predict the patterns, and mostly we deal with maps. But for me, that what was the changing point for my master's, because I didn't quite like maps, and map did not tell me the whole story I was about to find, because it's just green for me. It doesn't tell any information. So that actually brings me to my master's research, which moves from pixel-based classification to tree detection. So you can automatically see the difference in two images, right? When we use map, it's pixel. But when we use actual satellite imagery and we apply or harness the capabilities of AI, we can actually detect the trees and learn how we can impact the environment. So my master research title was GeoAI to implement individual tree inventory, framework, and application of heat mitigation. As I said, I'm a geographer and I love working with environment and heat and climate. So I actually call my journey to be a green journey because it's always related to tree and environment. So here, what I was doing, I was working as a research associate, and then I found that for urban cooling, we didn't really have the tree level data set that is needed to understand how trees are benefiting or contributing to the cooling. And that is because governments and planners, they actually go to the sites to field work, gather information about tree. Think about how difficult it is. You're going, you're collecting information. It's so costly and it's so time consuming. So how can we do that? Over the years, people have done it in this way. They have used maps, they have pointed out in map, georeferenced the tree on a map, but that is not scalable. And that's where my research comes in. I wanted to build an individual tree inventory and see how the species contribute to the cooling. Now, my study area was a small locality in Bendigo, and this is a satellite aerial imagery from 2018. So I mapped the heat and tree relationship for the time period of 2018. So due to the time, I had to focus on a small locality, unfortunately, but I feel like the workflow and the framework is scalable to any place, and planners and practitioners can adapt that. And my workflow, I'm not sure if it's quite visible, but it's divided in 3 stages. First, I used deep learning model to detect the trees. I built the inventory. Then I divided it in 2 models. Why? The first model was just about trees, its height, its species, and how much temperature in it. The second model was a zone-based model. I wanted to see the local relationship between trees and tree in respective of the built-up surfaces, so that I can understand how the cooling is actually working or how much impact it really has. And with these 2 models, then I applied spatial statistics and analysis to understand the correlation and the regression between the relationship. Now, the scary part was selecting the deep learning model. I was completely new. I had no idea about what deep learning was, what algorithm choose, and it's gone. Yes. Like this, my mind also went numb when I thought I have to do deep learning, which was crazy. So I heard about 3 different types of methods, which is YOLO. So I think every one of you are familiar with you only look once. And then it is a very accurate detector model, which works on, I think, moving images and videos. It worked very quickly. There is another model I saw was faster RCNN, because it had 2 detectors. One, it's the region, and once it gets the region, it goes into more details of it. And then I also had max RCNN, but the problem of max RCNN is that it has the same feature of faster RCNN, but it gives another marks per region or per pixel. Now, I wanted something which is fast as well as accurate. And it will give me the boxes for each tree crown and also give me the accuracy. That's why I chose faster RCNN. Now, it's not the best algorithm. I'm saying it's not the best, but for my data set, for my research, I felt that suited the most. So how it worked? I got the aerial image of my study area for Bendigo. Then I divided it into 100 by 100 frames. In each frame, I actually manually annotated tree species, and it was around over 6,000 tree species I manually annotated. And then I fed the model where the Inception ResNet V2, the backbone, acts as a feature extractor, so it gets the edges, the texture, the tree crown patterns and everything, and it holds the characteristics. Then it generates a feature map, which then goes through RPN, or region pooling network, which shows where the object can exist in that image. It still doesn't know where the species is, but it knows what part the object might fall. Once it's done, it moves to the ROI pooling, which then localizes the bounding boxes, and once that is done, the model kind of see what it learned as to what species it belonged to. Now, the crazy part was Bendigo has over 1,000 tree species. And it was, when I saw the species, I was flabbergasted. What's happening? Why so many species? So I took the first 7, not the first 7 I would say, but the most distributed one, the most prominent one in Bendigo, and I then, my FRCNN model predicted the tree crowns. As you can see, the bounding boxes. For each crown, it predicted each of the species, and it also gave me the accuracy of the detection for each of the species. So, I'm not sure if I can zoom in, but it's very blurry, but you can see like there are misses, but there are also hits, so you can see how the model worked. So for every tree species is detected, it gave accuracy metrics so that I can understand how my model worked. And overall, yes, my model for me worked really well. I got like 85.6 accuracy. I know many might think like it's less, but detecting a tree species is very hard, given the same species can have different color, different texture, different pattern. One good thing that I did was, my friend told me about transfer learning. So my ResNet V2 model was actually pre-trained on a COCO data set, and it was a tree data set, so it kind of like took up that visual features of the tree, and then I fine-tuned my model to my species, so it learned very quickly. I found that I heard like the machine learning models can be very difficult to run, and there can be a lot of problems, but for me, I really did not face such. It may be because, of course, my friends helped to tell me about machine transfer learning and to use pre-trained models, and it really eased up my work, and I could detect the tree species very easily. And once that's done, as I said, I built 2 models. The first model was just about the tree and its distribution, and the second model was zone-based model. If I can zoom in. So if you can see, each boxes actually represents small zones, because if we have large area, we don't really understand the different impact of the species. So that's why I divided into small zone, and then each, I'm not sure if it's visible, but the tree crowns are there, like the different colors, which shows different species, and then you see underneath our building architecture or building footprints. So I wanted to see how within this small boxes, the local relationship between the tree and the heat worked. So, it's not going. So, do trees cool city the same way? No, it doesn't. Tree does cool city, but species will differ, because species have their own distribution, own canopy size, own diameter. It will differ. And that's why we don't use a global model to understand this relationship. For decades, I have seen that the relationship is used like described in linear regression or Pearson correlation, but it's not enough. We need to go into more details as to what's going on. So that's why we have a spatial statistic called geographically weighted regression. Have anybody heard about GWR before? So that's GIS stats, and it's built by ISRI. So what it does is that it fit a local regression for each of the location, X and Y, and it just works the same regression way, but it's spatial. It takes every location. instead of running for the whole study area, it goes through every boundary, every inputs, and see what's the relationship between the independent variables and the dependent variable. So GWR in my model 1 told me that tree actually contribute to 94%, or it kind of like explained 94% of the variation of land surface temperature in Bentico. But then when I looked into the zone-based model, it became 85. And the cool part about using GWR is, I'll just go to the next slide. If I zoom in, it first gives one R-square, which is a local model fit, which tells how the model is performing across a study area. If it's red, that means the model performed well. If it's blue, it's kind of like, okay, I'm performing, but not so good enough. So it shows the goodness of the fit. So we can see like where the tree actually kind of like tried to have explain the variation of land surface temperatures, mostly around the middle section, the top section, and that also depends on the distribution of species. How we can see that, if I zoom into one of the tree, you can see for celery pear, which is species 1, it worked well where you can see the green areas are. Where it's red, it did not perform well. Again, 2 reasons. It might be the species are not distributed well, or it might be the crown size is small, or the height is small, or the diameter is small. So it can be various things. So similarly for other 7 species. The key part is, which I found that in my model, English elm, there is a species called English elm. It provided the strongest, or it predicted the strongest. Muga iron bark was the least. So my idea here is how we can use this AI and deep learning model to detect, and this can generate insights so planners can target, if English elm is providing or predicting land surface temperature, we might just focus on planting more of this species rather than doing a lot for others, right? So this kind of insights generally cannot be found in maps alone, as I go back to my speech. So that's why I want to focus on that. For our spatial research, we are moving towards harnessing these capabilities of AI and machine learning, and it can be scalable, it can be automated. We can find for the whole Victoria which species is working best, how it's distributed, how much cooling can it give, and not only cooling, shading, and so many other things. For pollution, trees also, in fact, for pollutions, for noise, there is so many research going on. So that's the summary of my master research. Now that I have done for neighborhood scale metrics, my PhD actually looks more closer to human exposure, because it's very close topic to my heart, because I've really faced it myself. Why, I will say, we are saying the cities are green, right? But can you really see the green from your building? And this happens because, as I said, cities are going denser. It's going vertical, right? Even if a park is there, it might be behind other building. So in the map, it can be counted as a green space beside in the neighborhood, but still be invisible to a lot of people. So I want to ask, how many of you see green, or a mix of green and gray, or gray from your apartments? So is it green? How many of you see green? Oh, green. And how many of you see gray, like complete gray? Does it really impact your mental health by any chance? Yes. This is actually a hidden or uneven reality we often overlook. A same apartment, if I show, it's in Docklands. This is my apartment. One side of my apartment is looking at complete view of nature, buildings, but the north side of the building is completely gray. So how would the person on the north side of the building feel every day waking up and looking at infrastructures and trams, right? So this is the reality actually we don't talk about. There have been many research that green benefits us. You should go to park, you should have more trees. We should have, but we should also see whether residents can actually see them. because it directly or indirectly impacts their mental health. Even for me, I was staying in Flinders, and in my Flinders building, it was completely blocked by buildings. I kind of had a very negative impact on my mental health. I didn't find it good. When I moved to Docklands, it's nature, it's beautiful. There's so many parks, there's so many playgrounds, and you can actually see them, although they are now again doing high-rising construction in front of my building and they're blocking the view. But I realized that that is something very important people or planners should take into account. And that's what my PhD research is about. How much greenery can residents see from the apartment and its impact on mental health? So currently, as I said, the data set that we have is neighborhood level. Some of the research are looking at building level data, like how much a building can see green, but it's still very coarse. I want to see apartment level. I want to see resident level. So how can we generate this? How much green residents see in this complex vertical environment? The approach, I have kept it simplified because I want my method always to be scalable and cost effective. So what I built was, I did simplified 3D models, not architectural, not design perspective, simplified models where I can point out the apartments. From there, I position, like you can see, it's written geocoding observer point, which means what I did from every window of the apartment, I took a midpoint of the lookout. Usually you stand and you look out, that becomes your midpoint. Now you might be thinking, why not the window? Why not the glazing? Again, that becomes very architecturally detailed. You cannot have so many attributes and still have your model scaled for the whole city. So instead, you develop this observer point based on resident-specific location. And then I built an environmental data set in 3 dimensions. I performed a spatial analysis called viewshed, which captures how much green, gray, and water residents can see. And that gave me a view composition, and with that, I linked to mental health. I'll go into more details of it because the data set actually mattered. So what I used was high resolution 0.8 centimeter resolution data set for modeling the environment. So it was in 3D. So all the process here, if you see, is that the data set was obtained from Urban Monitor, which gives us aerial imagery. So they kind of like captured the data set using stereo imagery techniques, and then they do the image reconstruction and give us the output data set. So once I got the output data set, I segmented it into 3 different layers: green, gray, and water. And then I reconstructed the urban environment in 3D. Then I built the 3D building models. Now here I used a different software called City Engine, which is an Esri-based software again. So City Engine actually allows to procedurally build a building from 2D footprint to 3D model. And again, you don't need like complex building information model. If you heard about BIM or if you heard about LiDAR, they're very complex, they're very point generated, so that takes a lot of time to kind of process that data set. Instead, you have the building footprint, you have the building height, you have number of floors, you can easily build the 3D model in City Engine. And then I actually manually verified with satellite images and Google imagery to see where the apartment positions are. And then the Victorian government have a standard spacing of 9 meters within each apartment. So to scale it, I actually use 9 meters. So every apartment is positioned at 9 meters. And the building that I focused on for my PhD, I actually manually cross-checked. Yeah, that is a bit of a difficult part. You have to manually cross-check and omit out the apartments which is not there, which is there, and then position it correctly. And that generated, if you can see, it's very tiny. For each point, the X, Y, and Z. The X is latitude, longitude, and Z is the height. So you have the X, Y, Z feature in 3D, and in the environment, the building models were placed. And then I ran a viewshed model. Now, how the viewshed model works? It's simple. From each point, a line of sight goes to the environment. It traces how much is visible. If there is any obstruction, the line will hit it, and then it becomes invisible. So you can see from this point of the building, the red part is the invisible part, and the green is the visible part. So I kind of used the same viewshed analysis used in GIS or geospatial research, but I automated it, I modified it. I modified it to my own apartment because viewshed analysis runs on, like, you can see 360 angle, which is not correct, right? Because you cannot see 360 from a building. So I kind of scaled it to each apartment location, its orientation, how much angle a person would look. I set up what we call FOV, field of vision. And then within that FOV, the line goes straight to the environment and calculates the visible and the invisible surface. And with that, I generated this is just a visual representation, like for each apartment points, now you have the view metrics, percentage of green, gray, and water. And oh yeah, I forgot to mention, it's not only green, I actually segmented my green into trees, shrubs, and grass. I also segmented my gray into high-rise and low-rise infrastructure because I wanted to find that fine detail as to what is happening in the environment and how much green are people seeing. So after I go to the mental health, but there was a fun thing I wanted to check, again, back to computer vision. So this is just one application, and I wanted to see how my model is performing. So I took an image from my building, and I came across this ontology-based SAM, grounded SAM, segment anything model. So there you give the prompt, the model will find out, localize the image, and it will generate mask for the feature that best suits the prompt, like you say, bunch of vegetation or a backyard full of plants. You can give prompt like this, and then it segments out the image. So I wanted to see from my building how much my model predicted. So in my observer-centered or individual, my model showed like 38.6% of green from my building, and in image segmentation, it's at 33.45. Same for gray, it's at 52.32, and my model said 55.89. So if you see the root mean square error, it's 3.78, which is kind of close to what my observer center model did. Now the problem why I did one image was that it's very hard to get image from all buildings. It is not possible, but if we can get image, it's one way of approach to validate our model and see what is happening. And this is another approach, like if we can take about for building to building neighborhood scale, we can actually apply SAM or computer vision model to get the view from a view from the building together, or view from the floors. So now it's just a quick thing. Now I'll go again to my buildings, my results. And same building, different views, as I said, because I found that most of the residents had over 73% of gray view and only 23% of green view. So you see, we say our city is green, but it's really not what people can actually see. And water features, I won't focus much on it because of the distributions of the buildings. Some places they have more water, so it's more about the data sets and the localization. So it's more about the gray and the green. And if you see for these buildings, if I bring in building 2, you can see from each direction or the side of the building, each apartment, how much the view is changing for green. This is just an example of the green view. The gray view and the water is not there, but you can see the view changing. And the cool part about my method is that this part of building 3, the northeast part of the building 3, was actually blocked by another building. So my model actually captured that because there was no greening in it. So that actually kind of proves my model is working, and I can use this individual level detail. You can see orientations, you can see apartment to apartment, you can also average out it floor to floor, building to building, neighborhood to neighborhood to see what is happening. And it actually gives insight to planners to see the inequalities that exist. And they can target actually greening where it's really needed the most, and not only just say, we need to plant trees, and focus on areas where it's really, really needed. And the second part is, of course, how the view relates to mental health. And it's true that greening will definitely improve our mental health. Although my data set is cross-sectional, so it kind of includes like causation, I cannot say that green view has impact, but I can say that green view was associated with mental outcome, and it had like 1.8% higher positive well-being than those in the gray environment. Then I actually did another part is view typologies, because people don't just see green, gray, and water. They see a combination of typologies, mixed environment. So that's why I used, it's not here, sorry, I used GMM, or Gaussian matrix modeling, a probabilistic cluster, which is a soft clustering approach that assigns the apartment residents into a group it might fall. So it's not like K-means, which is hard cluster, you have to be in the group, but GMM was the best approach because participants can have different typologies. And after I looked through the AIC and the BIC and the logs, 5 classes were the best suited. One is high gray. There is no much greening, completely gray. The second is urban composite, which has a little bit of green, but more high-rising building. Mixed density is more about mid-rise, low-rise building to like green environment. High green is too much of green. Of course, you need so much of plant. And nature dominant is you have a lot number of like the rivers, the oceans, the green, and kind of mixed balance of environment. So can anybody relate to any of the typologies you belong to here? Do you think it matches what you see or where you belong? So I use these typologies again to map out the relationship with health. And of course, people or residents who are in high green and nature dominant environment was higher or had higher positive mental well-being than those in the gray environment. I also link to psychological distress, but we don't focus more on the psychological distress part. It's more about the positive mental well-being which impacts. So yeah. Yeah, so actually my research is a part of a broader high life study which is done by my supervisor, Dr. Sarah Foster. So it's an ARC funded project, and they kind of run this survey for 3 metropolitan cities, that is Perth, Sydney, and Melbourne. And they got like bunch of self-reported data, not only on green, on everything, all the housing, how long they have lived. So that the inventory I got to use, and my project, actually my research comes from that high life study. And I haven't shown it here, but they have also captured resident self-reported perception. What I mean is that you usually go and ask how much green can you see in the building. So you might say 15%, 20%, right? And I actually modeled that subjective view to my measure, and I found that people really overestimate the greenery they see. Yes, you say like there is green, but no, my model found out one of the participants said they had 50% of greening, but my model found there is maybe like 28% of green. So that's why here I want to mention like there are self-reported measures to capture greening, but it can be recalled to like biasness. People can have different moods, can have different biasness or thoughts about it or different. So we don't have that quantitative measure. So that's where my research or my apartment green view measure comes in, which captures that quantitative green, gray, and water views from individual apartment residents. And with that, I'm kind of like in the talk. So my implication and direction is we always talk about having greenery, exposure to greenery, access to park, but I really feel that we should bring in the view concept into planning, because that will help in building design. And also like there's so much work going on in digital twin modeling and 3D cities, 4D cities. So if we can do some scenario testing, right? If there is a building and then we use the viewshed model and then we break the building, the building which is there, or build another building, we can see a what if scenario that is going on. And that can give the designers or the government to understand how we can better or create more healthier, more sustainable cities and societies. So thank you for listening. That's all from my research. And any questions? Any questions?
You mentioned GMM when talking about choosing the categories. What is that standing for?
Sorry?
The GMM?
Yeah.
Used to get the 5 categories?
Yeah.
What was that standing for?
So it's Gaussian matrix modeling. So Gaussian matrix modeling is like a clustering type, which assigns participants based on different group that they can fall in. So, yeah.
Awesome.
Can you say a little more about how the broader study measured mental well-being? Did they largely use self-reported measures, or did they use proxies?
No, the data set was self-reported measure, the mental health data set. It was participants' own data set. So because this is a cross-sectional design, as I said, like we cannot say that the green improves or the gray impacts psychological distress, but over time, the longitudinal studies which is done like over the years, they actually keep collecting the data from the same participants over the years, and then we can say how the mental health varies. So mental health component in my research is examining the association at an individual level, because when I looked at health data set or what's there, and when we connect that health to green, it is always that map and NDVI based measure. There was nothing at an individual level that can link to that individual self-reported mental health outcome. So that's what the model, if that answered the questions.
Firstly, just super impressive how you sort of looked at every angle on the problem and connected all of these different tools to bear on it. While we're talking about the well-being study, I was curious, the measure of green that people can see in that study, is that entirely self-report based on those categories? Or did you know their address and see like which window are they looking out of?
Yes, we have all the data sets on that. We have apartments, it's orientation, because when I linked my individual measure to resident, I needed that orientation or northeast angle, or is it the main window, is it the balcony? So everything has been collected in that self-reported perception. So they actually visited. Yes, they actually visited, but unfortunately I cannot show the buildings or disclose because it's under ethical consideration, so I cannot show too much details on the buildings, but yes, it's captured from people's home, yeah.
I remember a study from Harvard on forest bathing that was like walking through the forest and how it's beneficial. Has there been other studies that are more about like being able to look out and when you're not physically?
It's very less actually. That is why my research actually comes in. There was one study from China which was published. So there was 2 studies, one which is around 2000 and 1990, because if you heard about environmental psychology, there is a professor called Kaplan, and they talk about the view from home, but they are mostly theoretical, and over the decades they have been telling that we need to consider the view from home, but the measurement haven't captured that. So 2017 there was a study in China which looked at building level green. So they actually done from floor level. They did not account for apartment level. They said from each floor how much percentage of green is actually there. But then I expanded that study to apartment level to build this individual model to kind of say that you need to look from resident level perspective as well.
Is the outcome from this, you could then look at what is the highest leverage changes that you'd make to the area so that you impact as many people as possible?
Yes. Yes, you can. That's why I said like scenario testing. If we can model it for all the apartment buildings in Melbourne, we can see like how much greening they can see, and then we can like build accordingly. We can see like whether we need tree, because even I'm having the same experience. Like I said, I had a very nice view of the river and green, and suddenly there is construction going on, which I don't like. So it's blocking the view from like to the ocean sides or the beach sides. So they should consider people perspective. I really.
Also on the well-being metrics, like how much can you attribute a person's well-being on the amount of greenery that they see, or is it, or both of them correlate as two factors in which the rich usually they can purchase better service and they can choose where they live and
Oh, yeah.
also happen to
Yes, so I come across this question a lot because even my reviewers are talking about that, like people who are rich or young, they can find buildings. I have residence demographic data, and the numbers that I present is actually adjusted. So I run the linear regression, which is model 1, completely no adjustment, and then I adjust it for demographics, that is gender, age, their living with partners, income, education, and for my sets of participants, rich, I wouldn't say had much. They did have more green views, but it was more like distributed. I wouldn't like really say that they did, because it also depends upon the number of data sets. I'm working around 600 participants now, which is kind of less when this kind of questions comes up. But if we scale, then we can really find the pattern as to how much, like, whether the demographics really play a part in it. But yes, one distinction is, as you pointed out, thank you, the younger people do tend to live in gray environment than the older people. That is a difference I found.
Regarding the data set, we consider like with satellite images, it depends on the time of the day you take the image, and if it's like a day or a night, or if there's enough sunlight. So do you do like pre-processing on image?
No, I don't do the pre-processing of the image, but like I said, I mentioned Urban Monitor, so they kind of captures and have their own techniques of measurement. Of course, there are some temporal constraints, but the core part of my method is the scalability. So if we have like one set of thing ready, then we can apply this method to different, different temporal. Even I also thought about like seasonal variation in trees, right? The green will change over time. So I've thought about the seasonal variation, but it's like the time constraint. So I haven't got time to look at it. Maybe after my PhD, I'll look broader into that angle, what you said.
Based on your research so far, do you see a change with urban planners in terms of planting policy? Because I just noticed in the earlier slides, things like plants like English elms, like introduced plants, may have better cooling than, say, indigenous plants, which I'm not an urban planner, I imagine part of the choice of urban planners and developing smart notes because they support things like flora, fauna protection. So I just wondered what insights you want to develop at this point around policy.
Yeah, policy, yeah, they can, but I can't really comment on like the type of species because I've only worked with one study area and one species, and what, again, like I'm saying, my perspective is more about the application of method that the planners and practitioners, they can adopt it to see. So definitely they can use and see like whether the indigenous flora and fauna can contribute, but there is also another thing that is going on is the pollen. Like whether, even if we have species, like if we plant more species, do they contribute to a lot of pollen? They impact people's health. So there are a lot of various features and environmental features to consider when it comes to like planting. So yeah, that answer.
So in that sense, can you add other variables easily?
Yes.
So biodiversity or
Absolutely. In geospatial research, we work with a lot of data sets, multiple large-scale data set, biodiversity. There is another like team which is working on this kind of biodiversity, ecosystem management. There is another team working on the forest fire and management. So we can integrate everything in one and build a model. And that's why, like as I said, GeoAI, it's not only about algorithm, it's about how you apply algorithm in geospatial data, because geospatial data set has the capability to understand the environment and connect everything together. We just need to have better approaches, better mapping techniques, better algorithms to get that connection out. Oh, sorry.
You mentioned that you have annotated all the images. Have you used
No, manually. Yeah, I did know about there is like automated software. So after I have done it, I came across, and it was painful nights, sleepless nights. Annotation was hard because it goes wrong. Like sometimes you make it, and the tree species is actually very tricky because trees is okay. Species, you have to find out what species it is. You have to match the spectral differences, the points, its location, and mark it. So this is because my master project. So master project actually spans for like 2 semesters. So I've had like 6 months to finish it. So majority, like 5 months, I think went on like just doing the annotation and building the model because I was so new to it and I didn't know how to kind of do this kind of model. And my supervisor like gave up hope, like you might not able to finish your masters, just do the maps and go. I'm like, no, I'll never do the maps. So eventually it worked out. So yeah, I hope I knew about tools now that I come across. There's so many different tools that quickly, even AI does, I think, like automate the imaging process, everything, yeah.
So I was thinking about one question that might, on the second project, but might relate a little bit back to the first one. So I was looking at the technique you used to estimate the grain percentage. So it's more like a 3D modeling approach. So I assume the easiest approach would be treating grain patterns or like grain areas as like a region on the ground. Like, is that?
Sorry, which one you're talking about?
Basically, about estimating the grain you can see from a viewport. So I would assume you view the 3D model and like put a camera on like upon the windows and you see what the grain percentage. And I was thinking like, would that make a difference if you treat green areas as flat areas on the ground versus treating trees as having volumes?
Yes, it does make a difference, and that's why like there is a difference of 2D maps and 3D maps because tree crowns, their diameters changes, the height changes. So I'm currently actually researching on how this kind of height and diameter also contribute. And sorry, I forgot to mention a very important point as well. There is a concept of distance decay which I had it in my model, is that closer object plays more impact on your eyes than the distance object. So that's where the 3D is very important. 2D cannot capture that.
I've got an interesting question. Like, look at that picture.
Yeah.
And there's a window that's almost entirely blocked by the tree. Would you consider that a really high green percentage?
Yes, unfortunately, this is one of the, I would say, constraints of the data set, because if there is a green pixel, we would consider that it is a green. So if, like as I said, if we use LiDAR data set, we can actually demarcate like this might be blocking, this might not be a good tree. But again, handling LiDAR data set can be very tricky and very challenging, and it's not scalable across city, not at all. So yeah, that is one limitations of the approach, that if there is a green pixel, we would consider it green pixel. And of course, again, I said like this will contribute more to your eye than the distance one over there. Yeah. And there are more opportunities, like we can consider the branches, the barks, but these are all like out of scope during my research, so yeah.
So I hadn't quite picked up, so the first bit on Ballarat and tree species was your master's, and then it's the mental health and
View, yeah.
is your doctorate. Okay. Look, I'm very impressed with how a geographer has dived deeply into maths and models and just moved through stuff and learned some stuff. So I think I'm in awe and very humbled by it. A little bit of my background is around mining and people doing environmental studies in mining, and you might want to have a look across into that, because I know they built things where the drone flies through and they are building imagery and distilling from that density of vegetation as well as species, so that they can actually create baselines and say this is improving and it's getting more dense?
Yes.
Or no, it's dying off and it's
Yes.
thinning out?
Yes, definitely. Actually, geospatial is a very big part of mining research, but my interest is more about environment and people, so I wanted to go into that field. But mining is interesting because one of my friend was from Singapore and he was working in this mining and government project, and it's really interesting because their methods, I think, are a lot scaled up, like a lot advanced than what we have, and our is like still evolving. We are trying to kind of like bring in what in Australia specifically, because if I map out what I have talked, the advancement of AI and this spatial modeling evolved in China and US, but Australia still is like with the traditional maps and flat maps. So our idea is to bring more this algorithm 3D modeling, because we really need to see from the point of an individual, from in angle of 3D, because it's so complex, and reducing it down to the pixel doesn't tell us any story about it. So
The immediate commercial application seems to be the effect on property values.
yes.
Have you spoken to real estate or domain about it?
No, but there is one research which has used self-reported residence data and map out the property values in China. So as I said, the research are coming into Australia, so hopefully I'll do one of it, but property value is one of the application of such measure. Yeah.
So what was the correlation between the species and a particular location? Like, how did it improve or reduce the temperatures of the region? Was there any study on that?
Oh, so correlation, I mostly looked at the regression because that's the association to find out, because in geospatial research, we usually use regression to see the relationship change across space and area. So I haven't done the correlation, but in the regression part, what I said, like 95% or 96% is that temperature in that area is predicted by that species. So my land surface temperature is a dependent variable and my species are independent. So let's say celery pest species 1 is explaining 95% of the temperature in Bendigo. If it's Mugabark, maybe it is explaining 38% of the temperature in Bendigo. So we are using like a quantitative metric to kind of understand how the trees can have impact. Now, if we look more into details of cooling, like you say, we need to add like shadings and then road facilities, and research are going on that. Like there are so many research on shading and then heat and then solar panels and heats, like it's just vast. So sometimes like we have to constrain the research based on the time. So of course, like I have also this kind of feeling like, hope I could do this, hope I could that, but there's like time and limits to everything. So
Good luck.
In your master's work, when you're looking at the tree imagery, did you use other light spectra imagery as well? Like I know some of the other light spectra are better for detecting different types of trees.
no, I have used aerial imagery. I have actually looked at satellite. Yeah. Aerial. Yes, aerial imageries, because that was the only thing that was available during masters. So I looked at NDVI as well because the spectral reflectance from the satellite images, but it really wasn't enough. So then I thought about using the detection. So that actually pushed me to do AI and find out from the aerial image which was available to me. And yeah, because others are there, but they are very costly to kind of like get access to, or students don't have like quick access to those kind of data sets. So.